Alright, let's do some miscellaneous algebra exercises, and here's a good one. So, I'm not quite sure what they mean by this notation, so I'm not even going to touch it. I'm not even going to worry about it. So, let's just start with it. By the way, I have a solution written for this, but I have slightly different notation. So, hopefully this won't be a train wreck. I used capital X instead of capital S. So if I write this, what I mean is this. So anyways, since G is transitive, that means that the G action on S has just one orbit, i.e. G mod x equals 1. And here, by G mod x, I mean precisely the number of cosets. Right away. I mixed up, but yeah. So G mod s is 1, and by G mod s, I mean precisely the number of orbits that we get on from this action of G on s. So also, G is finite. I'm moving around my screen a little bit to find the best position because I'm using a new chair that will hopefully not give me permanent back problems. Anyways, and so Burnside's lemma applies. If you don't know what that was or what that is, it'll be implied by the statement because we're going to state what it means. It means that the number of cosets of this, or the number of orbits of this action is equal to 1 over the order of G times the sum for all G and G of x to the G. Seriously? Is this going to happen for the entire exercise? Hopefully not. Anyways, so this is what Burnside's lemma tells us. It means that if we have a finite group acting on a set S, I believe it has to be a finite set, but whatever. I mean, it's not whatever. Well, if it's not a finite set, can it, the number of orbits, be, well, whatever the case. I think it has to be finite. I think everything just has to be really nice here. So anyways, this formula holds. So in this scenario, we know that G mod S is 1, and so we just multiply the G over to the other side to get some G and G of S to the G, which, by the way, I'm just going to write this out in case this is a different notation. This is by S to the G, I mean the set of all S in S such that GS equals S. Note that, almost did it, S to the E is the set of elements. This is the set of elements that E fixes, and so E fixes everything, so it's just S, which is greater than or equal to 2. Okay, and now I'm going to do something special, something new here in this exercise. I'm going to actually use paragraphs, because I'm starting to realize that that's making some of these proofs really complicated or hard to read. So now assume for contradiction that there is no fixed, that show that there exists an element which has no fixed points. So assume for contradiction that for all G and G, did it again, S to the G is greater than or equal to 1, i.e. suppose that every element of G fixes at least one point. Then we do a computation. And so let's take the sum over all g and g of x to the g. Oh, God. This is equal to, well, let's see here. We know e is in g, so we can break that out. So, this is not going as well as I hoped. But, anyways, so we can take that special case where this special element e, and we separate that out. There, look, I wrote it. I wrote the capital S. And so what estimate can we do here? So this is certainly going to be, so s to the e is greater than or equal to 2. So this is greater than or equal to 2 plus, and then the remaining stuff is the sum over all g and g minus e. This s to the g, we know that's greater than or equal to 1, so it's going to be greater than or equal to if we just put 1 in there. And so actually, I guess that's a little bit unnecessary. We can just go straight away to this. It's going to be greater than or equal to the order of this set, g set minus e. And so what is that? This is 2 plus the order of g minus 1. This is just the order of g plus 1. Which contradicts that the sum over all g and g of s to the g is equal to the order of g. And so we have a contradiction, and therefore it is not the case that that for all g, s to the g is greater than or equal to 1, and so there must be some g such that s to the g is equal to 0, i.e. there must be some element which has no fixed points. And so, like, if you're actually writing out this proof, then you would write all of that out to wrap this up, but I'm not submitting this to anyone. I'm just submitting it to the whole world by putting it online, and so I'm going to be lazy and not write that out, but I explained it, and so you should know how to carry out the rest of this if you had to, and then that finishes this exercise. And so yeah, this is actually, I really like this exercise because I like analysis a lot more than I like algebra, and we're doing estimates here. Like here we know, we know s to the e is greater than or equal to 2, and we know all of these are greater than or equal to 1, and this is like a super rough estimate. It's like we're throwing out a whole bunch of information here, but we still retain enough information to give this estimate that gives us this norm g plus 1, which leads to a contradiction. And I don't know, I really like exercises like that where you're doing an estimate and you like throw out a whole bunch of information, like you get really, really weak bounds, and it just somehow is still, even though you're throwing out all this information, you still get enough information to give you the answer that you're looking for. So this, I like that this has a little bit more of an analysis proof to it, in my opinion. But anyways, so there we go. This is the proof.